Okay, this week we're talking about precipitation. So I thought I would start with radar. And since I have something on near my house, I am using Wakefield's radar. Wakefield's located right there. And my house happens to be right about there. So right now there's a thunderstorm that has developed over Norfolk, Portsmouth, Virginia. Very slow moving. But I wanted you to notice a couple things. This is precipitation type. Is derived from the dual pole radar, which means it's looking at both the vertical cross sections of a beam and the horizontal one. So it's seeing a shape, a two-dimensional shape, which was never available until we got dual pole. So with that, it can differentiate different types of precip. If I was to look in the very highest part of clouds, I would be seeing probably snow right now. But I'm not. I'm looking fairly low down. And what I'm seeing is several areas of heavier rain, which are actually moving towards the west, slowly and reforming out to the west with time. So it's kind of a neat thing that dual pole can do. If I were to show you reflectivity right now, and sometimes the National Weather Service radar page is kind of slow, I think, but there it is. You can actually see the thunderstorms and how they're moving and developing together. New ones are forming out to the west of where it was. And they're pretty intense, actually, fairly strong, but they're not moving very far. And you can see that one begins to dissipate, and this one begins to grow in its place right here, just a little bit to the south and west of where it was. And here's a new one developing out here in the southern part of Suffolk. So you can see almost a whole line of thunderstorms moving westward with time here. We're in kind of a tropical air mass, and that is right along the sea breeze. We've talked about sea breeze convergences. Right there is the perfect example of that. So with that, let's go back here now to what we're going to talk about: clouds, precipitation, and weather radar. So I've given you an example of how radar works a little bit here. So let's look more now at how we develop that precipitation. So how do clouds and precipitation form? We talked about the fact that water vapor condenses, becomes a droplet. Well, unfortunately, nothing's ever simple in the atmosphere. So, clouds, they're visible. They're droplets of water in the sky. However, guess what? Clouds can't form without condensation nuclei, which can be as simple as sea spray, maybe dust from the ground, a little bit of the roof, a forest fire, even chimneys. I'll give you a really good example that I came across when I was working in Charleston, West Virginia. There's a power plant that is Amos power plant. It's an electrical power plant, fairly clean, but it puts out a little bit of smoke, coal fired at the time. And with that, there actually can be a plume of clouds that develop because of the condensation nuclei and come downstream from that. And one time, it just sat there and it actually snowed under these clouds, 2 to 3 inches of snow right under the clouds that formed due to that smoke plume. So, why do we have to have condensation nuclei? Well, a raindrop is fairly large compared to a tiny little droplet. And when the tiny little droplet has such extreme curvature, notice the curvature is a lot greater the smaller the droplets are. Well, that means that they can lose the water molecules back into evaporation much easier. They can go back to vapor. So, in reality, we need to have a relative humidity of almost 300% to form a cloud droplet. However, these cloud condensation nuclei, when they're in the cloud, can actually dissolve into that first little bit of water and hold it together so that it can begin to grow. And with time, it gets large enough that it doesn't need that. And you can see here, flat surface, 100% relative humidity means one thing. A curved surface, especially a very, very sharply curved surface, means a whole different thing. That's the curvature effect. And the solute effect, on the other hand, is the one I was talking about, where you dissolve in these cloud condensation nuclei. So, water can be super cooled as well. There is kinetic energy in these little ice water things that kind of inhibit it from freezing when it's very, very tiny. Again, everything changes with scale. When we're large scale bodies of water, 32 degrees will freeze it. When you're a tiny little droplet in the cloud, 32 degrees does not freeze it. It needs something to help it freeze. Now we get to the ice nuclei, which can help it to freeze. So when that happens, we begin to transition to ice over the whole thing, and we eventually create snowflakes, which may fall to Earth. Gravity has to overcome the resistance, so it's going to reach what they call terminal velocity and just keep falling at that speed after a certain point in time. So there are two different ways precipitation forms in clouds. Most common way is the Bergeron-Findeisen effect. However, in warm clouds, and I was just literally showing you some fairly warm clouds, even though eventually the Bergeron-Findeisen effect does apply to thunderstorms, the lower level of that cloud probably is having collision coalescence. What happens is temperature is above freezing, or at least the clouds haven't become iced. When that happens, a little droplet gets a little bit larger and begins to fall. It hits other droplets, grabbing them, pulling them in, and they get bigger and bigger till you get a raindrop. These processes occur in a warm air mass, so there's lots of moisture. They also occur very efficiently to make raindrops. So you wind up with some of the heaviest precipitation under these kind of processes. They happen in the summertime, especially around hurricanes, and in the tropics a lot. However, most of the time, Bergeron-Findeisen is going to take the cake with what we wind up with. So at some point, ice nuclei are going to hit and begin to freeze those little tiny water droplets that are out there. When that happens, we talked about it earlier, the kinetic energy is greater, just a little bit greater in the water compared to the solid ice. What that means is water vapor pressure is a little more to saturate it over the water droplets than over the ice crystals. So the water vapor is going to tend to flow from the water droplet to the ice. So the ice crystals are going to grow, and that is going to cause snowflakes that can fall, and it's also going to cause everything to begin to freeze up at that level. That's the Bergeron-Findeisen effect. And you can see the tiny little snowflakes gradually grow in size. Almost all precipitation that we get starts as snow. It'll eventually melt on the way down, but it begins as snow. However, if it gets really dry in the bottom layer, in the desert sometimes, even here I have seen instances where we have a dry air mass and you can see precipitation falling out of the clouds, but it doesn't reach the ground. It's virga. Here are some examples: rain, drizzle. Drizzle is just tiny little raindrop, really very, very tiny droplets. Interestingly, snow can be different shapes. We always say no two snowflakes are alike. Well, that may be true, but they're very different in size too. Dendrites, fairly large actually. Then there's thin platelets or sectored plates, etc. There's some more dendrites that are different. They depend on the temperature that they form at. So if I were to show you and tell you you're going to get a 1/4 inch of precipitation, and that's all going to be snow, but those snow instead are going to be all hollow columns or solid prisms. That will make a much smaller accumulation than if I gave you all dendrites with more fluff. So when we're forecasting snowfall for your area, we have to determine which of these types is most likely to be occurring most of the time. Adds another challenge to snowfall forecasting. Here you can see what happens to precipitation as it's coming down to the ground. If you're cold all the way down from the ground and the Bergeron-Findeisen effect has occurred, guess what? It's all snow. If on the way down you hit a warm layer, and remember, warm air can ride over cold, so you may have warm layers along. What happens is it doesn't take a lot. It only takes about 2 to 3 degrees Celsius above freezing, and at about 200 to 300, about 1,000 feet, we can melt all the snow into rain. So you've just changed the whole snow into rain. Now below that, if it gets very cold again, which does happen, it will freeze back into sleet. And if it's way down towards the ground where it actually gets cold enough, it may be freezing rain. Or if it stays warm the whole way down, it's rain. So you can see we look at soundings, and we've talked about skew T's and Stuvie diagrams and all. And here's a classic one. Temperature gets above freezing here, just enough. And below that is very cold air mass. So what happens? You get a very thick glaze of ice. All right, I've already went through radar, different modes of it. Reflectivity mode is basically looking at the echoes. Velocity mode is I can detect air motions with it. Just like if I hear a train going by, it changes the way it sounds. Well, the same thing happens with radar, radio waves. And here's the radomes that you see. And there's that Doppler effect again. And finally, here is an example of picking out a tornado. If you got knowing the motions, what I'm looking for is one part of the precipitation moving one direction and one part moving another. And the closer they are together, I see a tighter and tighter circulation. And here is a hook echo that shows up many times around this circulation. And if they're very strong, there could be very, very intense tornado. Here, dual pole. It's an amazing process dual pole does for you because it really helps you pick out debris, for example. It can also give you a heavier rain. So it really influences how you look at the radar and what you can see now. Phased array radar. I'll never see it in my lifetime. I'm not even sure you're going to see it ever utilized. It costs almost $1 billion per radar, and you would need hundreds of them to cover the U.S. So it's not something that's in anybody's budget. However, it's continuous. In other words, I got to use it and play with it on the one that the Weather Service has in Norman, Oklahoma, and you wind up, you can actually see everything going on in the whole column of the atmosphere instantaneously. And with that, it means I can see instantaneously rotation beginning maybe in the upper part of the cloud, or maybe where the actual freezing level is changing, all instantly. Whereas the rotation that I have with all radars now, they do a scan up and then they scan back down. So you're not seeing it. It may happen in 4 minutes, but that's not the same as instantaneous. And here you can see rainfall estimates from radar. Finally, we're just going to talk a little bit about cloud types. I love to look at clouds. There are cirrus clouds, high wispy ones. We've talked about that. Stratiform, which are just layers, and cumuliform. And we can see cloud streets that come off the mountains as well, and off in the lakes and stuff. So hope you got a little bit out of this. Let me know if you have any questions here.